Hi, Rich Neapolitan back. The last two talks concerned the applications of logic in artificial intelligence and informatics. Today, I'm switching to probability. This is actually my field, probability and Bayesian networks, and so now it's a greater chance you're going to find I actually know what I'm talking about. I guess I knew what I was talking about before, but I'm a lot more comfortable talking about this stuff. All right, let's review reasoning under uncertainty a little bit first. The knowledge-based systems that we discussed use logic to perform certain inference. All conclusions were reached with certainty. We knew for a fact that the class was gymnosperm. We knew for a fact that the family was Cypress. There was never any uncertainty. Even when we were doing diagnosis, we concluded, according to those systems anyway, for sure that the problem was spark plugs, or whatever the problem was. In many domains, especially medical diagnosis, we are uncertain about our conclusions. For example, we may just conclude that it's very likely that the patient has strep throat. We don't conclude that for sure. I had a funny or interesting experience with a clinician once. I had the flu, and I eventually got a bad sore throat, and I thought I may have gotten a strep infection also. So I went to my clinician, and he gave me a test for strep throat, and it came back positive. And I wanted to try to conclude how likely it was I really had strep throat, because I didn't want to take antibiotics for no reason. So I asked him about how good the test was. I wanted to know things like the true positive rate and the false positive rate. We'll be talking about those things, by the way, if you don't know what they are. And he said, well, these tests are made by Abbott Labs, and they're a good company. So I kind of concluded that this was a clinician who needed a course like this one, perhaps, which is becoming more prevalent in medical schools, something such as formal methods for reasoning under uncertainty. All right, so let's go on. Researchers initially tried to handle uncertainty by staying within the rule-based framework. This was a natural thing to do. The rules handled certain inference, so why not use them to handle uncertain inference? The pioneer in reasoning under uncertainty in artificial intelligence in general and in the medical domain in general is Edward Shortliff, who was at Stanford. In my mind, I could almost consider him the father of medical informatics. He developed the Meissen system in the 70s to diagnose bacterial infection while reasoning under uncertainty. Meissen uses the rule-based approach while handling uncertainty with what Edward Shortliff and his colleague Buchanan called certainty factors. In the 1980s, it was realized there were serious problems with this approach. I'm not going to cover the approach. It's actually in the contemporary artificial intelligence text, and not a lot, but I do discuss the problems there, and you can read about them if you are interested. But I want to cover the approaches which are modern day and which are being used and which we have not perceived problems. I do want to say that Edward Shortliff did something very important by starting us reasoning this direction, and in fact it was his students, Gregory Cooper, Eric Horvitz, David Heckerman, who in the 1980s, with a number of other people at the Uncertainty in Artificial Intelligence workshop, realized that the certainty factor approach was not the approach to use, and it gave birth to the field called Bayesian networks, which we're going to be covering, and which I wrote about in my 1989 textbook that summarized all these results. All right, so in fact it was David Heckerman, a Shortliff student, who wrote one of the most important papers showing what was wrong with certainty factors. And so Edward Shortliff was a great pioneer for moving us in this direction, and he was actually one of the people who helped move us away from certainty factors and into the Bayesian network approach. All right, probability methods based method using Bayesian networks, which I've talked about a couple times, which we'll cover in detail eventually, were developed. I'm going to present that Bayesian network approach. And I'm going to start today by just reviewing probability. A lot of this you already know, but I still think it's of value to review it because I want to review it within the Bayesian framework. And there's some of it I believe you probably do not know already. All right, here's something that is right out of a probability textbook. What is a probability function? We have a set of elementary outcomes. All right, a classic example is two outcomes, which could be heads and tails of a coin toss. Another example would be 52 outcomes, which could be which card is drawn from a deck of 52 cards. I'm going to be using examples of an ordinary deck of cards. So I'm going to be assuming that you know what they are, and if you don't, try to become familiar with them. It's a card that's got 13 different values, an ace through a king, and 4 different suits: clubs, hearts, diamonds, and spades. All right, so try to get familiar with that before you proceed with this talk. All right. Every one of these events is assigned a probability, which can't be smaller than 0, can't be greater than 1. The sum of all of them has to be 1. And the probability of a subset is the sum of the probabilities of its members. So if we take 3 of these events, I've just taken 3 arbitrary ones as an example. In this case, it's E3, E6, and E8. The probability of that event, that subset, is the sum of these 3 probabilities. That actually is all there is to the formal definition of a probability function. As important as probability is, it's largely just based on this relatively simple definition. Here's an example: the coin toss. The space is 2 events, heads and tails, and we assign them each 0.5. Now, we always assign probably heads 0.5, probably tails 0.5, but is that really what we have to do? It works for a symmetrical coin, but what if we were flipping a thumbtack? A thumbtack can land on its flat end, which we call heads, or it can land with the edge of the flat head and the point touching the ground, which we call tails. And some people might want to assign them each 0.5, but that really isn't quite what we mean. When we use a probability, we usually want to somehow measure the likelihood of the event happening, and if this is a tall, skinny thumbtack, it's less likely to land heads than if it's a short, fat thumbtack. So we need something more than this equally likely probability assignment, and that's the relative frequency approach to probability. It was developed by Richard von Mises in the early part of the 20th century, and it says the probability of an event, in this case heads, is the limit as n goes to infinity of the number of times heads occurs, that's what Sn is, divided by the number of tosses. So let's say we toss this thing 10,000 times and the thumbtack lands on its heads 3,761 times. Then the probability of heads is about equal to 0.3761. So in order to really know, according to this approach, to know a probability, you have to do something a lot of times. This is standard statistics. How do we estimate the probability of a smoker having lung cancer? We take a lot of smokers and see what fraction get lung cancer. So this is the way standard statistical methods always handle probability. I'm going to actually, there's a separate whole talk devoted to the meaning of probability, and so I'm going to get back to this more then. Now I just want to go on with some of these definitions and how to use them. Here's another example. If we have 52 cards, like I say, we assign the probability of the Jack of Hearts is 1 over 52, all right? And the probability of a Jack, then, we assign every card probably of 1 over 52. I just mentioned the Jack of Hearts. They're all assigned 1 over 52. And then according to that third criterion for a probability space, probably the Jack is the sum of the probability of the things in the set of Jacks. Probably the Jack of Hearts, there's probably a Jack of Clubs, there's probably a Jack of Spades, there's probably a Jack of Diamonds. So we add up 4 1 over 52s, and the probability of a jack is 1 out of 13. Now, how does this assignment of 152 fit into that relative frequency approach to probability? Well, this is actually done based upon what John Maynard Keynes called the principle of indifference. You may know John Maynard Keynes more, especially today, because of Paul Krugman talking about him quite a bit as being the founder of Keynesian economics. But he was a great economist, but he also was a probabilist, which people don't know as much. And he, in fact, coined this term, the principle of indifference, which means if you have no reason to choose one outcome over another, you assign them the same probability. The case of tossing what looks like a fair coin, we have no reason to pick heads over tails, so we assign them both probability 1/2. The case of choosing the top card from a deck of cards, we have no reason to choose one outcome over another, so we assign them each 1 over 52. And if you, in fact, run experiments with these kinds of situations where it's reasonable to assign the principle of indifference, and do them many, many times, the limiting frequency definition agrees with this. Actually, a jack of hearts does come up about 1 out of 52 times. Who did these experiments? Well, there's a guy named Carrick, John Carrick. In the 1940s, he was a conscientious objector to World War II, so he's a mathematician, and he was put in jail. Now, what do people do when they're in jail? I mean, a lot of people will lift weights or play basketball, but this guy's a mathematician. I mean, not as likely to be people lifting weights. So he ran a bunch of these experiments. That's how he spent his time. Eventually published a paper in 1946 when he got out, showing that probabilities assigned with the principle of indifference do agree with that relative frequency approach to probability. All right, let's go on now and talk about a very important concept in probability, conditional probability. The conditional probability of E given F, written probability of E given F, is the probability of E happening given that we know F occurs. All probabilities are really conditional in information. For instance, when we assign a jack of hearts, the probability of 1 over 52, that's based on the information that it's one of the 52 cards. But this means additional information within what we've already assumed. Let's look at this. The probability of a jack, as we already mentioned, is 4 over 52, or 1 out of 13. The probability of a jack given a royal card in the same domain is different because now there are only 12 royal cards. There's the 4 jacks, the 4 queens, and the 4 kings. 4 of them are jacks, so that's 1/3. These are different. This is additional information which has changed the probability of a jack. It's made a jack much more likely once we know it's a royal card. Independence. If the probability of E given F equals the probability of E, if F does not change the probability of E, then E is independent of F. As we noted before, the probability of jack is 4 over 52. But the probability of jack given a club, well, there are 13 clubs, and 1 out of a jack is 1 out of 13. It didn't change the probability. In terms of betting, if you were trying to ascertain whether this thing was a jack, and somebody had the information as to whether it was a royal card, that would be of value to you, because it could change the probability from 1 out of 13 to something much more likely, 1 out of 4. But finding out it's a club doesn't change the probability of a jack, so it's really meaningless information as to whether it's a jack. You know if it is a jack, it's a jack of clubs, but that's not what this event is. It's knowledge of a jack, and it hasn't changed. Now, what I've talked about so far, many of you probably already know. You know what a probability space is, you know what independence is. A concept which is not as well known in an ordinary probability course is conditional independence, but it is important in Bayesian networks. So it's important that we get this straight. Two events E and F are conditionally independent given G if once we know G, we take the probability of E given G, right? Now we find out F also. And if the probability of E doesn't change, then E and F are conditionally independent once we know G. Notice regular independence simply does not have this G here. It's probably E given F equals probability of E. Now we are conditioning on G, and once we know G, finding out F does not change the probability of E. Here's an example where to make this very concrete, I made up this urn type example where we have these 13 objects. They can either have a color, which is black or white. They can have a letter, which is A or B. And they can have a shape, which is square or circle. There's 3 qualities they can have. The probability of an A is 5 out of 13. You can just do that by adding up. There are 13 events. 1, 2, 3, 4, 5 of them are A's. Probability of A given a square, well, there are 2, 4, 6, 8 squares. 3 of them are A's, so it's 3/8. Notice that these are not independent, by the way. A and square are definitely not independent. Finding out a square changed the probability of an A. But let's restrict ourselves to black items. The probability of A given black, there are 2, 4, 6, 8, 9 black things. 1, 2, 3 of them are A, so it's 3/9, or 1/3. Now we're in the domain of black items, and we find out it's a square. So it's a black square. There are 6. 1, 2, 3, 4, 5, 6. So there's 6 items in the denominator, 2 of which are A, so it's 2/6, or 1/3. So A and square are independent given black. These numbers are the same. A and square are not globally independent. So it's a case where 2 variables are not independent, but they're conditionally independent given another variable, namely black. Same thing holds for white. If we're in the domain of white objects, the probability of A is 1, 2 out of 1, 2, 3, 4, 1/2. If I intersect the things that are both square and white, there's 2 things, and one of them is an A. So A and square are not only independent given black, they're also independent given white. So far I have used the set notation used by mathematicians for improbability. The random variable notation is much more convenient for our purposes. In the text, Contemporary Artificial Intelligence, I rigorously go from the set concept to the random variable concept. Here I'm going to do it more loosely, and intuitively it's somewhat easy to see what a random variable is. I let C be a random variable for color. So C equals black or white. So that means we can talk about the probability of C equal to black. The probability the color is black. We can talk about the probability C equals white. The probability the color is white. S be a random variable for shape. In other words, instead of talking about the probability of a square, we can talk about the probability that the shape equals a square, or the probability that the shape equals a circle. And V be a random variable for value. We can talk about the probability of V equals A, that the value is an A, and the probability that V equals B. All right, so the random variable notation, as you'll see, will become is much more convenient in the kinds of applications we'll be doing, rather than talking about the probability of a set. So you can talk about the probability the color is black, probably the color is white, probably the shape is a square, probably the shape is a circle, probably the value is an A, probably the value is a B. The random variables V and S are conditionally independent given the random variable C if for all values of the random variable the probability of value given shape and color equals probability value given color. Here's one particular assignment of values. The probability the value equals A given the color equals black is 1/3, right? Because when color is black, there are 9 things, 3 of them have A. Probably value equals A given color equals black, and we know the shape equals a square. There's 6 objects here, 2 of them have value A, so it's also 1/3. So these 2 are equal. In order for these 2 random variables, value and shape, to be independent given color, we need to have this equality hold for all 8 combinations of values of these. All right? We've shown that it holds for this one, and actually before I showed it that it held for another combination when the color was white and the shape was square and the value was 8, but you need to show it holds for all 8 of them. It actually does hold for all 8 of them. You can check that in your leisure hours if you like. It'd probably be a good idea maybe to perhaps check it. And it does hold for all 8 of them, and so we write that value and shape are independent given color. Once you know the value of the color, finding out the value of the shape does not change the value of the value. Actually, use another word, the value for that. All right, so value and shape are independent given color. All right, for the probability distribution defined by these particular set of objects. Here is an interesting application of this. Let's say we have 12 individuals, and they have 3 attributes. We can know their gender, which is female or male. We can know their height. In this case, they can be 64 inches tall, 68 inches tall, 70 inches tall. We know their salaries. In this case, that's $30,000, $40,000, or $50,000. And let's just say these 12 individuals are indicative of an entire population. In other words, we could take this, multiply it times 1,000,000 perhaps, and find that these are the probabilities amongst everybody in some population or city or state or whatever. Wage and height are not independent. Probably wage equal 30 is 1/4. Probably making $30,000 is what? Well, there are, how many? I'm missing some. There's 1, 2, 3 people making 30,000. There's 12 people, so it's 3 out of 12, or 1/4. Probably wage equals 30,000. Here I abbreviate, here I did not. That's a little bit careless, I guess. Probably wage equals 30,000 given the height is 64. Well, if we were in the 6 people who are 64 inches tall, there's only 6 of them, 2 of them make 30,000. So it's 2 out of 6, which is 1/3. So if you're short, you have a greater chance of making less money than if you are average height. If you are medium height, if you're in these 4 medium height people, only 1 person makes 30. So now the probability of making the small money has gone down a little. And if you are tall, there's nobody who makes 30. And if you look at these data, you'll see that taller people are not only less likely to make 30, they're more likely to make 50. All right, so this just eyeball with, if we ignore this variable and just had a statistic on height and wage, we see a correlation between height and wage, and you would tend to start believing that tall people are more likely to get higher salaries. You'd even look for a causal relationship here, that employers look at tall people and they're more likely to promote them and pay them more. All right, and people start wearing lifts in their shoes. I mean, just so they would look taller, so they'd get more salary. This works, I think, for actors. I actually had a friend who made a movie. He played thugs in movies. His name's Bob Zadar, and he made a movie with Sylvester Stallone named Tango and Cash. And my friend's real tall. He's 6'3", about 6'2" or 6'3", and he told me that Sylvester Stallone wore lifts in his shoes. That Sylvester Stallone was only 5'7", and with these lifts made himself 5'10". All right, so certainly Sylvester Stallone could not appear to be 5'7" next to my 6'3" friend. He'd look too small in the movie. I mean, so for him, that is advantageous to wear those lifts, and it helped his career of playing Rambos and Rockies and the like. But for a computer programmer or a professor, is there really any advantage to being tall? Well, these data seem to indicate that. But we are ignoring this variable when we make those kinds of conclusions, which is what was done, actually, I should add this, in statistics for a while until people became more aware of the kinds of things we're talking about right now. Wage and height are conditionally independent given gender. In other words, once we condition on gender, these two variables lose their dependence. Pi wage equals 30 given gender equals female is 1/2. Once we're up here, there are 6 women, 3 make 30. Pi wage equals 30 given height equals 64 and gender equals female. Once we're in the shorter females, there are 4 people, 2 make 30, it's 1/2. Pi wage equals 30 given you're one of the taller females. There's 2 of them, 1 makes 30. And in fact, this is true for all combinations of the variables. Again, there are 8 combinations, and no matter what we put in here, all right, these values are always equal to these values. All right, once I condition on this, finding out the value of height does not change anything. And wage and height are independent given gender. Again, you could check this out in your leisure hours. It might be a good idea to actually do so. Let's just go beyond the numbers and think a little bit, what does this mean causally? Well, the reasonable conclusion from this would not be that height makes you taller, but there's discrimination in the workplace. Women are more likely to be short, and women are more likely to make less money. Again, no conclusion from a statistical observation can be made for sure, but that is the more reasonable conclusion, and that's going to get us into Bayesian networks eventually. This kind of idea of these notions of statistical independence, but we have more probability to cover first. All right, that's the end of the show. Next time I will be talking about more probability, in particular Bayes' theorem, which is very important in probability.